In question 1, we've got a train traveling along a straight horizontal track between stations A and B. We start from rest at A, accelerating uniformly for capital T seconds, reaching a speed of 20 meters per second. We maintain this speed for 3 minutes and then we decelerate, coming to rest at station B. We are told that the magnitude of the acceleration of the train is twice the magnitude of the deceleration, and we need to sketch a speed-time graph to illustrate the motion from station A to station B. So we start from rest, we accelerate, and then we maintain the speed, and then we decelerate. The speed reached is 20 meters per second. The acceleration here was for capital T seconds. We maintained this speed for 3 minutes, so 3 minutes is 180 seconds. So the time here is capital T plus 180. And we've been told that the magnitude of the acceleration is twice the magnitude of the deceleration. So if we've been accelerating for capital T seconds, it means that we've been decelerating for double this time, so 2 capital T, which means that the time at the very end is 3 capital T plus 180. We are additionally told that the distance between the two stations is 4.8 kilometers, and we need to find the value of capital T. Well, we know that the distance covered is the area under the speed time graph. So in our case, we are talking about meters. So 4.8 kilometers is 4,800 meters, which is equal to the area of the trapezium here. So we're looking at base 1, which is 3t plus 180, plus base 2, which is simply 180 over 2, times the height of the trapezium, which is 20. So this leads to 4,800 being equal to 3t plus 360 over 2 times 20. So the 2 with the 20 will simplify to leave me with a 10, and then the 10 with the 4,800 will simplify, leaving me with 480 on the left-hand side. So we're looking at 480 is equal to 3t plus 360. So we have 120 being equal to 3t, and therefore capital T is equal to 40. In part C, we need to find the acceleration of the train during the first capital T seconds of its motion. So looking again at our speed time graph, the acceleration is the gradient. We've got a rise of 20 over run of capital T. So the acceleration will simply gonna be 20 over capital T, and we just found capital T to be 40, so 20 over 40, which is equal to 0.5 meters per square second. In question 2, we've got two particles A and B moving in a straight line in opposite directions on a smooth horizontal surface. When they collide directly, we are told that the particle A has a mass of 3m, whereas the particle B has a mass of m. Immediately before the collision, both particles are moving with a speed of 1.5 meters per second. After the collision, the direction of motion of A is unchanged, and the difference between the speeds of A and B is 1 meter per second. We need to find the speed of A and the speed of B immediately after the collision. As always, I will start by drawing the two particles A and B. We've got the masses of 3m and m here. We've been told that they were moving towards each other with the same speed of 1.5 meters per second. And after the collision, the direction of motion of A is unchanged. So A is still moving to the right. I'll call it speed V. So we are also told that the difference between the speed of A and the speed of B is 1 meter per second. Now surely B must be moving to the right, because if it was moving to the left, it had to pass through A, which is physically impossible. And also, since B is moving to the right, it must have a speed which is greater than the speed of A. Otherwise, A would have to go through it, which is also physically impossible. So B is moving to the right with a speed of V plus 1. This means we can proceed with the conservation of linear momentum. So the momentum before was 3m times 1.5 plus m times minus 1.5, which is equal to the momentum after, which is 3mv plus m times v plus 1. So we're looking at 4.5m minus 1.5m is equal to 3mv plus mv plus m. So we're looking at 3m is equal to 4mv plus m, leading to 2m being equal to 4mv. Obviously the m's will cancel out, and we get that v is 0.5. This is the speed of A after the collision. Now for the speed of B after the collision, we simply need to consider that V plus 1 is equal to 0.5 plus 1, so that's 1.5 meters per second. In part B, we need to find in terms of M the magnitude of the impulse exerted on B in the collision. Well, we know that the impulse is the change in momentum, and if we consider particle B, the momentum after the collision is m times 1.5 minus the momentum before, which is m times minus 1.5, because before the collision the particle was moving to the left, which is the negative direction. So this is equal to 1.5 m plus 1.5 m, which leads to 3 m Newton seconds. In question 3, we've got a particle P moving with a constant acceleration of minus 4I plus j. Initially, at time t0, the velocity is 14I minus 5j, and we need to find the speed of P at time t is 2. So I will start by quoting that V is u plus at, where v, u, and a are all vectors. So the initial velocity is 14 negative 5. This is the velocity when t is 0, plus 2 times the acceleration of negative 4, 1. This will give me the velocity when t is 2. So 14 plus 2 times negative 4, which is negative 8, leaves me with a 6, whereas the negative 5 plus 2 times 1 is negative 3. This is the velocity, but we've been asked to find the speed, and the speed is the magnitude of the velocity. So this is going to be 6 squared plus negative 3 squared and all square root. This gives an answer of 3 root 5 meters per second. I can leave it in exact form, or I can give it as 6.71 meters per second. In part B, we need to find the size of the angle between the direction of the vector I and the direction of motion of P at time t is 2. Well, we know that the direction of motion stems from the velocity. We found the velocity when t is 2 to be 6 negative 3. So this means I can quickly draw a vector of 6 negative 3. We go to the right and down. We are looking for the angle between I and the velocity vector. So I is the vector going to the right. So we're looking at the angle shown as theta here. Well, this simply leads to tan theta being equal to 3 over 6. And therefore theta turns out to be 26.6 degrees. In part C, we're told that when t is capital T seconds, P is moving in the direction of 2I minus 3j, and we need to find the value of capital T. Well, we know that the velocity is the initial velocity of 14 negative 5 plus the acceleration of negative 4, 1 times the time capital T. So we're looking at 14 minus 4t and minus 5 plus t. If I'm moving in the direction of 2 negative 3, this means that the velocity vector is parallel to 2 negative 3, which leads to 14 minus 4t over minus 5 plus t being equal to 2 over negative 3. I will cross multiply to get negative 3 times 14 minus 4t is equal to 2 times negative 5 plus t, leading to minus 42 plus 12t is equal to negative 10 plus 2t. Well, I will collect the t's on the left, leading to 10t being equal to 32, and therefore capital T is 3.2. In question 4, a branch AB having a length of 1.5 meters is resting horizontally in equilibrium on 2 supports. The supports are at C and D. We've got the distances shown here. When a force of 150 newtons is applied vertically upwards at B, the branch is on the point of tilting about C. We are modeling the branch as a non-uniform rod having a weight of W newtons. We are told that the distance from the point C to the center of the mass is x meters, and we need to use the model to find the value of W and the value of x. So let me start by adding the forces here. We've got the weight of W, we've got the 150 newtons acting vertically upwards at B, we've got the reactions at C and D. I will also add the distances from C here. So the distance of the center of mass, capital W, from C is x, and the distance of the 150 newtons from C is 1.26, found by doing 1.5 minus the 0.24. we know that we are on the point of tilting about C. So if I'm about to tilt about C, it means there is no reaction at D. And therefore we can proceed by taking moments about point C. So if we take moments about C, we've got the clockwise moment due to W, which is X times W, so XW, which is equal to the anti-clockwise moment, which is the 150 newtons times 1.26. So this is equal to 150 times 1.26, leading to XW being equal to 189. Additionally, we are told that when a force of 225 newtons is applied vertically downwards at B, the branch is on the point of tilting about D. So we need to use this second piece of information to see exactly what's happening. So I'm adding the extra force of 225 newtons downwards at B. Obviously, the 150 newtons is no longer there, and we are on the point of tilting about D. So if I'm about to tilt about D, this means that we've got a reaction at D, but we now don't have a reaction at C. So the plan is to take moments about the tilting point D. So I need to find the distance between the center of mass and D. So this distance here is simply going to be 1.5 minus the 0.24 and the 0.36 and the X. This leads to 0.9 minus X. And therefore we can proceed by taking moments about D. We've got the clockwise moment, which is 0.36 times the 225, being equal to the anti-clockwise moment, which is 0.9 minus X times the weight of capital W. So we're looking at 81 being equal to 0.9 W minus XW. Well, we know that XW is 189, so we're looking at 81 is 0.9 W minus 189, leading to 270 being equal to 0.9 W. Well, if I divide both sides by 0.9, I get that W is equal to 300, and then I can proceed in substituting W with 300. We get 300X is equal to 189, and therefore X is equal to 0.63. In question 5, we've got 3 points P, Q, and R lying on a straight line. Now the distance PQ is 6x meters and the distance QR is 5x meters. A vehicle is moving along the road from P to Q with constant acceleration. When t is 0, we are at P with a speed of u meters per second. When t is 12, we are at Q with a speed of 2u meters per second. And we need to use the model to show that x is 3u. The first thing to do is add the information on the given diagram. So t is 0, we are at P. T is 12, we are at Q with speeds of u and 2u respectively. Well, we know that since we are moving with a constant acceleration, we can use the Suvat formulae, and we know that S is equal to u plus v over 2 times t. So in our case, we have covered a distance of 6x, which is equal to the initial speed of u plus the final speed of 2u over 2 times the time of 12. Now, obviously, the 2 with the 12 simplify to give me a 6, and we are looking at 6x is equal to 3u times 6. So 6x is equal to 18u, and therefore x is equal to 3u as required. We then have that as the vehicle passes Q, the acceleration changes instantaneously to 1.5 meters per square second, and the vehicle continues to move with this constant acceleration of 1.5, passing through point R with a speed of 3u meters per second. And using this model, we need to find the value of u. So looking again at our diagram, the new information is that between Q and R, we've got an acceleration of 1.5, and we are passing through point R with a speed of 3u. Well, we know that v squared is equal to u squared plus 2as, which means that 3u all squared is equal to 2u all squared plus 2 times 1.5 times the 5x, which is the distance covered. So we're looking at 9u squared being equal to 4u squared plus 15x. So we've got 5u squared on the left-hand side, and on the right-hand side, I will be replacing x with 3u we found in part A. So 5u squared is equal to 45u. Now I will simplify the 5 with the 45, leaving me with a 9 on. Now I will simplify the 5 with the 45, leaving me with a 9 on the right hand side, and the u squared with the u, and therefore we conclude that u is equal to 9. In part C, we need to find the distance traveled by the vehicle during the first 14 seconds after passing P. So the first thing to do is find the value of x. We knew that x is equal to 3u, and we just found that u is equal to 9. So x is 27. This means that the distance PQ is equal to 6x, so 6 times 27, which gives a distance of 162 meters, which corresponds to the distance covered in the first 12 seconds of motion. And then from t is 12 up to t is equal to 14, I will be using s is equal to ut plus a half at squared. Well, we know that the initial speed was 2u, so this is going to be 2 times 9 times the time of t plus a half times the acceleration of 1.5 times the time squared, so 2 squared. This gives an answer of 39 meters, and therefore the total distance covered is 162 plus 39, which is equal to 201 meters. In question 6, a boat is pulled along a river at a constant speed by 2 ropes. Now the banks of the river are parallel, the boat is traveling horizontally in a straight line. The tension in the first rope is 500 newtons at an angle of 40 degrees to the direction of motion. The tension in the second rope is P newtons acting at an angle of alpha to the direction of motion. We've got a resistance to motion of magnitude 900 newtons. We are modeling the ropes as being light and lying in a horizontal plane, and we need to use this model to find the value of alpha and the value of P. Well, the first thing to do is add the forces acting here. We've got a resistive force of 900 newtons, so this is opposing motion because the boat is moving to the right. And then we've got a resolving of the 500 newtons. Well, vertically here it's going to be 500 sine 40, and similarly for P, the vertical component will be P sine alpha, and the horizontal components acting to the right will be 500 cos 40 plus P cos alpha. Now, since the boat is moving at a constant speed, it means that there is no resultant force, and therefore I could equate the upward with the downward forces, and then the forces to the right with the forces to the left. So we've got 900 being equal to 500 cos 40 plus P cos alpha, and for the vertical forces we've got 500 sine 40 is equal to P sine alpha. Remember, we're trying to find alpha and P. Well, from the first equation I will isolate P cos alpha, so we're looking at 900 minus 500 cos 40 being equal to P cos alpha. And then if we consider tan alpha, this is equal to sine alpha over cos alpha, and would be just great if there was a P here and a P here. So P sine alpha over P cos alpha corresponds exactly to the expressions we just obtained. So P sine alpha is 500 sine of 40, and P cos alpha is 900 minus 500 cos 40. So this gives an answer of 0.62167 ... and therefore if I do shift tan of the 0.62167, we get that alpha is equal to 31.868 ... and therefore we conclude that alpha is 31.9 degrees. We can easily then proceed in finding P. I could substitute alpha here, so we've got 500 sine of 40 being equal to P times sine of 31.868 ... This leads to P being equal to 609 newtons. In question 7, we've got the simple lift shown here operating by means of a vertical cable. The lift has a mass of small m. We've got the box Q placed on the floor of the lift and the box P placed on top of box Q. We are assuming that the cable is light and inextensible, and we're completely neglecting air resistance. We are told that the tension in the cable is 42 mg/5, and the lift and the contents are moving with acceleration 2g/5. We need to find, in terms of small m, the combined masses of boxes P and Q. I will start by adding the forces acting here. We've got the tension of 42 mg/5 acting upwards. We've got the weight of the lift itself, which is mg, and we call the combined mass of P and Q to be capital M. We've got the weight of these two boxes being capital mg, and the lift together with the contents are accelerating upwards with an acceleration of 2g/5. So I will simply do forces acting upwards minus forces acting downwards is mass times acceleration. So we are looking at 42 mg/5 minus mg minus capital Mg is equal to m plus capital M times 2g/5. Now the first thing we notice that there's a common factor of g, and we cancel this out, and then I'll be multiplying everything by 5, leading to 42m minus 5m minus 5 times capital M is equal to 2m plus 2 capital M. So we're looking at 37m minus 5 capital M is equal to 2m plus 2 capital M. So we have 35 small m is equal to 7 capital M, and therefore the value of capital M, the combined masses of P and Q, is equal to 5m. Now during the motion of the lift, the force exerted on box B by box Q is 14 mg/5, and using the model we need to find in terms of m the mass of box P. So this is the situation we had up to now. We will be concentrating on P and Q to see exactly what's happening here. So if we consider what P is feeling, P is surely feeling its weight, so I will call its mass P, so the weight is Pg. It's feeling a reaction due to the contact with box Q, and this reaction has a magnitude of 14 mg/5. The whole thing is accelerating upwards with an acceleration of 2g/5. So we consider P, we've got forces acting upwards, which is 14 mg/5 minus forces acting downwards, which is Pg, is equal to P times 2g/5. I will multiply throughout by 5 to get 14 mg minus 5 Pg is equal to 2 Pg. Obviously the g's will cancel out, and therefore this leads to 14m being equal to 7p, and therefore 2m is a value of p. In question 8, we've got a parcel of mass 2 kilograms being pulled up a rough inclined plane by the action of a constant force. This force has a magnitude of 18 newtons and it's acting at an angle of 40 degrees to the plane, as we can see on the diagram. Now the plane is inclined at 30 degrees to the horizontal. The coefficient of friction is 0.3, and we're modeling the parcel as a particle. We need to find the acceleration of the parcel. So we know first of all that the parcel is moving upwards with an acceleration a. That's what we're trying to find here. We will add all the forces acting here. So we start with the weight of 2g, which I will be resolving as 2g cos 30 perpendicular to the plane, and 2g sine 30 down the plane. And we also have got friction because the parcel is moving upwards. Friction is that force which is always opposing motion, so friction is acting downwards. What we are missing is the resolving of the 18 newtons here. So we've got 18 cos 40 up the plane and 18 sine 40 perpendicular to the plane. And of course we've got a reaction force because of the contact of the particle of the parcel with the plane. So this summarizes all the forces acting on the system here. Now to proceed and find the acceleration, let's consider that the forces acting perpendicular to the plane should be balancing out. So we've got 18 sine 40 plus the reaction force R being equal to 2g cos 30. So this means that the reaction R is equal to 2g cos 30 minus 18 sine 40. We also have that the friction has attained its maximum value, so F is equal to F max, which is equal to mu R. Well, mu has been given to be 0.3, so F is 0.3 R. And then we can proceed with the forces acting along the plane. So we've got 18 cos 40 acting up the plane. So 18 cos 40 minus the forces acting down the plane, which is 2g sine 30 plus F being equal to mass of 2 times the acceleration of A. So this means that 18 cos 40 minus 2g sine 30 minus F is equal to 2A. I will replace F with 0.3R, so we're looking at 18 cos 40 minus 2g sine 30 minus the 0.3, and the R is 2g cos 30 minus 18 sine 40. All of this is equal to 2A. So if you plug everything on the left hand side on your calculator, you get 2.3676 being equal to 2A, and therefore the acceleration works out to be 1.18. In part B, we have that the points A and B lie on a line of greatest slope of the plane, where AB is 5 meters and B is above A. Now particle P passes through A with a speed of 2 meters per second in the direction AB, and we need to find the speed of P as it passes through B. So where exactly do we stand now? The situation is something like this. This is point A, this is point B. We know we are moving upwards with an acceleration of 1.18 ... I will be using V squared is equal to U squared plus 2AS. So we're trying to find the speed of P as it passes through B. So V squared is going to be 2 squared plus 2 times the acceleration of 1.18 ... times the displacement of 5, because we have been told that the distance from A to B is 5 meters. So this leads to V squared being 15.838 ... and therefore if I take the square root, V turns out to be 3.98 meters per second. Now the force of 18 newtons is removed at the instant when P passes through B, and as a result P comes to rest at the point C. Now we need to determine whether P will remain at rest at C, and we must show all stages over working clearly. So we start by drawing a diagram here. We've got the weight of 2g, which I will be resolving as 2g cos 30 and 2g sine 30 down the plane. We obviously have got friction, which is opposing motion here. So without friction, the parcel would slide down the plane. So the friction is acting up the plane. And then we've got the reaction R. I will start by equating the forces acting perpendicular to the plane. So R is equal to 2g cos 30. Now I don't know whether P, the parcel, will remain at rest or whether it will start accelerating down. So what I will do, I will find the maximum frictional force, F max, which is equal to mu R. This is equal to 0.3 times 2g cos 30, which is equal to 5.09. The force down the plane is 2g sine 30. And 2g sine 30, if you plug it on the calculator, turns out to be 9.8. Well, we observe that the 2g sine 30 of 9.8 is certainly greater than the maximum frictional force we can have of 5.09, and therefore we conclude that since 2g sine 30 is greater than F max, P will start sliding down the plane.